Hello, Assalamualaikum warahmatullahi wabarakatuh. So, we are here to present about Lagrange theorem. There is statement of Lagrange theorem. First, if G is equal to a subgroup that is generated by A is finite, the order of any elements divides the order of the group. This implies if H is a subgroup of A, then we know that H equal to A power of M for some M element of Z, and the order of H is equal to the order of subgroup that is generated by A power of M and equal to the order of A power of M divides the order of A that is equal to the order of G. Thus, the order of any subgroup divides the order of the group. The order of the group represents the number of the elements. Next, if we look at the second statement, that is, let H is a subgroup of A, then we know that H is equal to A power of M for some M that is element of Z, and the order of H is equal to the order of subgroup that generated by A power of M and equal to the order of A power of M divides the order of A that is equal to the order of G. If you look at the diagram below, we can see there is element of G. There is H, A1 times H, A2 times H, A1 times H, A2 times H until AM times H. There is left coset of the group. So there is element H in the group of G, and if we add element A1 times H and A2 times H, there is not overlap with the H and it has the same size. So it can be divided by the element, the order of the group.
Next, we will talk about the properties that we should know to prove this theorem. The first thing is coset. The definition of coset is stated like this. Let H be the element of G and let A be element of G. Then we define HE and AH like this. HA is equal to HE, H element of H, and AH equal to AH, H element of H. There are also properties where if G abelian, then H is also abelian. Show that if H equal to H1, H2, and Hn, then HA is also equal to H1, A1, H2, A2, and Hn, An. And AH equal to A1, H1, A2, H2, and An, Hn. These are for multiplication properties. For addition properties, we show again that if H equal to H1, H2, and Hn, then H plus A equal to H1 plus A1, H2 plus A2, and Hn plus An. And also for A plus H is equal to A1 plus H1, A2 plus H2, and An plus Hn. So we can conclude that HE subset or equal to G and AH is also subset of or equal to G, since if IH is element of G for all I, then IH is also subset or equal to G for all I. Same goes to AH, where AH is element of H for all A, then AH is also subset of or equal to G for all A. That is equivalent relation. Let S be a set and with dash be a equivalent relation on S. If A and B are two equivalent classes with A intersect with B equal to empty set, then A is equal to B. The definition of equivalent relation is a relation on a set generally denoted by with dash that is reflexive, symmetric, and transitive for everything in the set. We can look at the reflexivity for A equivalent relation to A, symmetry if A equivalent to B, then B equivalent to A. And lastly, for transitivity, if A equivalent to B and B equivalent to C, then A equivalent relation to C. For example, the relation is equal to donated by disabled is an equivalent relation on the set of the real number seen for any x, y, z element of G. Reflexivity S equal to S. Symmetry if X equal to Y, then Y is equal to S. And lastly, transitivity if X equal to Y and Y is equal to Z, then X is equal to Z. Next is a bijective, injective, and surjective. Injective, a function where if and only if is hit element in the codomain at the most on one time. For example, if fx equal to fy, then x equal to y. For contrapositive, also prefer if x is not equal to y, then fx is not equal to y. Surjective, a function where if and only if every element in codomain hits by the function. For example, let f e to the b. For y element of b, there exists an x element of a such that y equal to fs. And lastly, bijectivity, a function that is both injective and surjective. We can say that there is an one-to-one correspondence between its domain and codomain. For example, the function f r to the r defined by fx equal to x cubic is bijective.
So next, let's prove the Lagrange theorem. So, let H be any subgroup of the order n of a finite group G of order m. Let us consider the cost breakdown of G related to H. So now, let us consider each coset of AH comprises n different elements. So, let H equal to bracket H1, H2 until Hn. Then AH1, AH2 until AHn are n distinct member of AH. Suppose AHI equal to AHJ and HI is equal to HJ. Be the cancellation law of G. Since G is a finite group, the number of discrete left coset will also be finite, CP. So, the total number of elements of all cosets in NP, which is equal to the total number of elements of G, hence M equal to NP. Because of this, P is also equal to M divided by N. This shows that N, the order of H, is a discrete of M, is a divisor of M. The order of the finite group G, we also see the index P is also divisor of the order of the group. Hence, this proves that the order of G is equal to the order of H group.
Lagrange theorem corollary. First corollary. If G is a group of finite order M, then the order of any A subset G divides the order of G, and in particular, A power of M equal to E, or identity. Let me prove. Let P be the order of A, which is the least positive integer. So, A power of P equal to identity. Then we can say A power of 2, A power of 3, A power of P minus 1, and A power of P equal to identity. The elements of group G are all distinct and forms a subgroup. Since the subgroup is of order P, thus P the order of divides the group G. So we can write m equal to np, where n is a positive integer. So a power of m equal to a power of np equal to a bracket ap power of n equal to identity. So it's proven. Okay. The second corollary, if the order of finite group G is a prime order, then it has no proper subgroups. Let me prove. Let us consider the prime order of the group G is m. Now m has only two divisors, 1 and n. Prime number property. Therefore, the subgroups of G will be identity and G itself. So there are no proper subgroups. It's proved. The last corollary, a group of prime order, the order has only two divisors, is a cyclic group. Let me prove. Suppose G is the group of prime order of M and A not equal to E subset G. Since the order of A is a divisor of M, it is either 1 or n. But the order of A, O bracket A not equal to 1, since A not equal to identity. Therefore, the order of O bracket A equal to P, and the cyclic group subgroups of G generated by A are also of order n. It proved that G is the same as the cyclic subgroup formed by A. So G is cyclic. It proved. Thank you.